We now have topologies for clock and data recovery with forwarded clock, but we have to analyze these things quantitatively, and we do that in the phase domain because that's what is important. Meaning the whole idea of the clock and data recovery is that you adjust the position of the clock so that it is in the right phase to sample the data, and the phase is what is important. Okay, so the waveform of course has to be appropriate for the circuits to work, and usually if you have a squarish waveform, that's what is good enough. As you go to higher frequencies, it becomes difficult to have a square wave, but if you try to get a square wave, that's good. But what's important is the timing as far as the current discussion is concerned. So we need to have phase domain models for all of these things. So, and to be able to do this, we need to understand this phase in some depth. First, we will consider like periodic functions. And let's say I use this as example, like let's say cos theta or sin theta, but it can be any function that is periodic with 2 pi. It will all the arguments that I make now will apply to that in the same way. Okay. Okay. In fact, like I said, you typically see square waveforms in the serial link in the high-speed data communication domain. But as far as the phase is concerned, taking any function of period 2 pi is fine. And because this cos theta is so familiar, I'll use that. Okay. And if you really want to, you can always take the sinum of this, which turns this into a square wave. Okay. So this is a function periodic in theta. Right. So this means that for any n, this is the definition of the cosine function, right? So now let's say this theta is of this form. It is let's say it is like this. Okay, where t is time and this theta is some proportionality constant omega naught times time. Okay. Then if you look at the same function, cos theta is cos 2 pi f naught t. So now this is a constant. Okay. Omega naught or f naught is a constant. So now this also becomes periodic in time. Okay. Right. So when you are asked to give an example of a periodic function in time, this is probably one of the things that comes to mind first, right? Cos 2 pi f naught t. So this cosine function is always periodic in its argument. Okay. As the argument increments by 2 pi, you will get the same value again. Okay. But now if that argument theta is proportional to t, okay, then it also becomes periodic in time. So let me plot theta versus t, and this means that I have some slope and the slope is omega naught. Okay. So now I know that basically this function is periodic with a period 2 pi, right? As theta goes from 0 to 2 pi to 4 pi, 6 pi, 8 pi, etc. The function repeats. Okay. So now if you look at the time instants at which it crosses this 2 pi, 4 pi, 6 pi, etc. Because this is a straight line, these intervals, the time intervals when the function takes function repeats the value is also, they are also equal to each other. Okay. So that's why this is periodic in time. Okay. So and what is this interval? Obviously it is 2 pi by omega naught or 1 by f naught. Okay. So if the phase is the phase theta, total phase theta is a linear, varies linearly with time, then the function is also periodic in time, and the period is 2 pi by omega naught or 1 by f naught. Okay. We will see why we are doing this so elaborately. It is something, it appears to be something quite simple, but okay. Is this fine? Now of course I can add an offset. So let's say it is some phi naught I have. Okay. Instead of theta being 2 pi f naught t, I have a constant offset. What happens then? So this will shift. Okay. So then also you see that when y-axis crosses integer multiples of 2 pi, it will separate these time intervals which are also equal. As long as this is a straight line, you will have equal intervals. So this also is periodic in time with the same period. Okay. Is this fine? Now if the slope changes, what happens? If it's a straight line but the slope changes, what happens now? So again, you see that to cross 2 pi you need to go a longer time. Okay. So this, again, this is something obvious, but I am just showing it to you with this diagram, right? So a smaller slope means a smaller frequency. That means that it takes a longer time to complete this 2 pi radians. Okay. So this obviously has a longer period. So if you plot the total phase of a periodic signal versus time, it will be a straight line, and the slope is the frequency, the radian frequency. Okay. Longer time intervals for 2 pi phase interval. Okay. We are doing all of this because we need to deal with signals which are intended to be periodic. Ideally they are periodic, but in reality they deviate from periodicity by some extent. Okay. So this kind of picture helps us visualize all of those things. And also sometimes you have to deal with signals of different frequencies, and one way to think about them is you have the phase that is incrementing at different rates. Okay. So this understanding of this phase is very important for understanding of clock and data recovery circuits and phase lock loops and so on. Okay. Where essentially the phase of the signal is important. Okay. This is fine. So next we will introduce one more term to the phase. So let's say I now consider theta to be so the first part is this is a ramp. It just is related to the frequency, and then you have a phase offset which is just related to where it starts off. Okay. So it doesn't change this from being a straight line, but it changes the values at that instant, but it is still periodic. And then plus, let's say I have some other function of time, which is not linear obviously, because if it was linear, if it was a straight line, I would absorb it into this and change f naught. Okay. So for now, let's assume that all the straight line variation, the linear part is absorbed into this, the offset is here. So this phi of t, typically, I mean this is not necessarily true. Sometimes we take this phase, this is known as, this is the additional phase deviation. Okay. So this phase deviation doesn't necessarily have to eliminate all the straight line parts and so on. If it is, it means that the frequency has changed. But many cases we consider this to have zero mean. That is, the average frequency is captured here and the phase offset is captured here, and any deviation is in this one. Okay. So now let's say this phi of t, this is phi of t alone. Okay. It can be anything. Phi of t alone versus time, if I plot it, it may be something like this. Okay. I'm showing something small. So then the total phase, it turns out to be something of that sort. Okay. So again, this function is periodic when theta, for theta with a period of 2 pi, right? So that means that when this theta crosses integer multiples of 2 pi, you finish one cycle. But now this is no longer periodic in time, because when this crosses 2 pi, first time you have this interval, and when it crosses 4 pi, you have a longer interval. When it crosses 6 pi, you may have a shorter interval, and so on. Okay. So, and because of this phase deviation, for every 2 pi increment of phase, you have a different time interval. So this is not periodic. Okay. So this is not periodic in time. Right. So basically, signal, I mean, in fact, the way I have drawn it, it's almost periodic, but then there are some small deviations from that. Okay. And this part can be called as phase deviation or phase noise if it refers to random quantities. Okay. Or sometimes in the modeling you have some frequency error or phase error, it corresponds to that, and so on. Okay. So if this phi of t, if this is a constant, then the result is still periodic with time. Okay, that just represents a phase offset. That's why I typically absorb it into this. If it is a straight line, then again that corresponds to a signal of a different frequency. Okay, because I'll absorb that into the first term. But then it could be neither, in which case the signal is not periodic in time and you have these deviations in the period. Okay. Is this okay? So now how are these things related to each other? This theta of t, this is the total phase, is 2 pi f naught t plus some phi naught plus some phi of t in general, okay, or omega naught t plus some phi naught plus phi of t. Okay. So this is the total phase. Now if you differentiate this with respect to frequency, you will get omega naught and plus any deviation due to that one. Okay. And of course, if this will just be omega naught if you don't have this phase deviation. Okay. So to get the frequency from the phase, you have to differentiate it. That's all. This is something that you know. Or if you want this is known as this is the radian frequency. Okay, number of radians per second. Or you can have this this gives you F naught, and this is the F naught if phi of t is 0. This is known as the cyclic frequency, basically number of cycles per second. Okay. This is fine. So now, if you know the phase of some signal, you can find its frequency. The frequency can be constant, in which case you have a periodic signal, or the frequency can have a constant plus some time varying part, in which case you actually have an aperiodic signal, right? This essentially means that the frequency is changing with time. Okay, that's why this is called the instantaneous frequency. Okay. And also, if I assume that the average of d phi by dt is 0, that is averaged over time, so then this F naught will be the average frequency. Okay. So what is the average frequency? So what is frequency after all? It is the number of cycles per second. Okay. So now let's say you have 1 billion cycles per second. You can only say that its average frequency is 1 gigahertz. Okay. Because those cycles may not be of equal length, right? So if the cycles are of equal length, then of course it is perfectly periodic with a frequency of 1 gigahertz. But if the cycles are not equal to each other, over 1 second period, the average frequency is 1 gigahertz, but the cycles could be varying with each other. Okay. So if this d phi by dt has 0 average, which is typically how it will be especially when we consider noise, then this F naught represents the average frequency, and this represents the frequency deviation. Okay. So this is the frequency deviation. So any of these measures could be used to represent the aperiodicity of the signal. Because if you have one, you will get the other. For instance, this we have already considered, right? This is the phase noise, essentially. Okay. And this analogously, this will be the frequency noise or the frequency deviation. Okay. Sometimes it's called residual FM and things like that. Okay. They're all, they're not independent. They're all related to each other. Sometimes you specify phase noise, sometimes you specify frequency noise. Is this okay? So now, based on this, you will have a number of different measures, which are all again related to each other, but any of which could be used to specify the deviation from perfect periodicity. Okay. We have already seen phase noise, but all these other things can be also used. Okay. So for instance, one of the ways is to measure these intervals, the time intervals for which you have 2 pi phase interval. Okay. So that is essentially you measure the length of each period. Okay. So I will call it phase noise, although it may represent other kinds of frequency deviation. You may call them noise, you may not. And then okay. This phase noise, you show its spectrum with this phase noise spectral density L of f. Okay. So this is a frequency domain description. The phase noise, the way we do it, we specify spectral density, so it's a frequency domain description. Now you also know about jitter, which is a time domain description. Okay. So again, what is jitter from here? These intervals for which phase increments by 2 pi, they should all be equal to each other. You somehow measure some difference between the ideal and the actual cases. Okay. In reality, the intervals will not be equal to each other. Okay. So then you have a number of measures in the time domain. So for instance, you have the period jitter. This is basically actual period minus the ideal period. Okay. And then you have absolute jitter, which is what we have considered earlier. This is actual instants of crossing those intervals of 2 pi minus the ideal instants where you cross that 2 pi. Okay. And it's easier to just say actual edge positions minus ideal edge positions. Okay. And then you also have what is known as cycle to cycle jitter. We'll later see, see if we can find context to all of these things. These are all, again, these are all describing the same thing. The reason you have so many metrics is some of them make sense to us in some context and some others are more convenient in other contexts and so on. Okay. The cycle to cycle jitter is basically the length of the current period minus the previous period. Okay. It's the first difference of the cycle length. Okay. Maybe this period is 1 nanosecond, the next period is 1 nanosecond plus 10 picosecond, then the cycle to cycle jitter is 10 picoseconds. Okay. These are, I am just giving you the definitions. These are again some things that you would know, especially from basic communications type courses, but we are revising these things. Okay. Any questions here? Now one thing that we commonly do is to represent this phase, as I have done here, as a continuous time signal. That is, I have plotted theta of t where t is continuous, right? In reality, you can measure the phase of a signal only at the transitions. That is, you have to mark off some value and you have to see when the signal crosses that value. Like for instance, you have a sinusoid and you see when it crosses 0. Okay, maybe in the right, you can take either only one direction or both directions. But let's say you take only one direction, then the distance between them will be the period, right? So phase is inherently a sampled quantity because of this, right? So you can measure the phase only by looking at the position of the edges. But for a lot of analysis, it is convenient to think of this phi or theta as a function of continuous time. Okay, so that's what we will do. But sometimes you may have to use samples of this to look at what is happening at the point of interest. Okay, so what you really want is essentially the ideal edge position is here. Okay, and the actual edge position is there. You just want to know the phase deviation, right? Is it okay? Now, both descriptions in the discrete time as well as continuous time are useful. Continuous time is easier to use and analyze, and it's usually valid when you are dealing with frequencies much smaller than the sampling rate. And the inherent sampling rate of this is basically the frequency of the signal itself, or maybe twice that, because periodic signal, it will have at least two edges, right, within a period. So it's either the signal frequency or two times that one. But we've already seen cases where you have to use the discrete time description. Where is that? Like when you found out the phase noise of a divider, for instance, right? The jitter is a discrete time function, and what is this divider doing? It is dropping samples of that discrete time function, right? It is taking one out of so many samples. To compute the spectral density, you had to use that description. Okay? You assume that the output jitter has the same variance as the input jitter, but it will have only one out of every m samples, and then found the spectral density and so on. Okay? So we'll use both, but the continuous time stuff is used to model things like the clock and data recovery circuit, etc. Even there, the discrete time model may be essential in some cases, but the continuous time model is easier, and we'll start with that. Is this okay? So just to find the relationship between the two, so let's say theta of t is 2 pi f naught t plus phi naught. This is the ideal. Let's say theta naught of t, that is without jitter or phase noise. This represents the phase of a this represents the phase of a perfectly periodic function, right? And the actual theta of t, let's assume that the average frequency and the phase offset is the same, but you also have phi of t. Okay? So now, what is the jitter? If you want samples of the jitter, how do you get it from this? Theta of t by? Two pi f naught times? No, this is phi of? What is kT? When do you have to look at what are the sampling instants now? K by f naught. When this whole thing, this is equal to k times 2 pi, right? That's when you have basically the zero crossings, right? Rather, okay, it depends on whether it's a sine or a cos. So if it is sine of this theta naught of t, then it will have zero crossings at this. Actually k times pi. If it is cos, you will have plus pi by 2. Okay? So you have to find out when the ideal zero crossings are, okay, and find the value of this at that zero crossing. So what I am trying to say here is the following, right? Let me draw this here with slightly exaggerated phase deviation. This just represents 2 pi f naught t, okay? And then let's say this represents 2 pi f naught t plus the phase noise, okay? I have of course exaggerated the phase deviations here. And these are 2 pi, 4 pi, 6 pi, 8 pi and so on. So now you have to do this many times. So this is the ideal instant, that is the actual instant, and this is the jitter. Okay? So what you have to do is you have to find out when this function crosses integer multiples of 2 pi, when this other function crosses integer multiples of 2 pi, and then find the difference between those instants. Of course, solving for that is very difficult. To find when this The first one is easy, but to find when the second one crosses integer multiples of 2 pi is difficult. But of course, when jitter is small, essentially what you do is the following. So here I am plotting only phi of t, okay. So phi of t, this is just phi of t, okay. So now, I mean, solving for this instant is very difficult, right, okay. So what you do is the following, and this works as long as the jitter is small and it has some limited bandwidth, so that basically over that small deviation it doesn't change by too much. So you find, so this was the ideal one, let's say this was T naught, then you find phi of T naught, okay, then what? That is the phase at this instant. How do you find the jitter now? When this phi of T naught is small, how do you find the shift in zero crossing? So let's say a signal is like this, right? The phase was marching off like this and it crosses 2 pi at this instant, okay. And then let's say I add a constant to it. For now you assume that I have added a constant. So the result will be something like that. So how much is this deviation? Huh? How much is the horizontal deviation? What's that? Yeah, that divided by the slope. Okay, this works only as long as over that deviation that you calculate, the phase itself hasn't changed much. Because I mean the way I have shown it, that's not the case, right? I have shown a very large deviation to be able to draw it. But when the jitter is small, basically this jitter equals the phase sampled at T naught divided by the slope 2 pi f naught, right? Is this clear? So this works only as long as, I mean, over that interval which is the jitter, which is the displacement, the phase hasn't changed much. And for small jitter, this works out fine, okay? Because if you have, let's say, 1 picosecond of jitter, your phase hasn't changed all that much by that 1 picosecond. That is the continuous time model of the phase. What I am trying to say is that if you, once you have this phase deviation, what you have is not a periodic signal in time at all, okay? In fact, the values of phi that are of interest are non-uniformly sampled. But if you uniformly sample it at the ideal zero crossing instance and divided by the slope, you will get the deviation. This is a very commonly done thing. I mean, this may be a point of confusion, that's why I am mentioning this. Okay. So tau of k is basically phi of there may be some phase offset here, okay, or time offset, but it is integer multiples of T naught, where T naught is the period of the signal, where T offset represents, I mean, T offset is the offset to adjust for the phase of the signal, whether it is cos or sine or something else, okay, divided by 2 pi f naught. Yeah. It could be random, yeah. No, I mean, this is the relationship. If you know that value, you can write it like this. So then, if you know the value, you can write it. Otherwise, you have to use statistical measures. If this is noise and phi is random, this jitter also will be random, that's all. Okay? Is this fine? So this is the relationship between different quantities. Now we will try to model the CDR, basically the clock and data recovery circuit, get the incremental model of it, and then see how, I mean, and from there we can calculate everything, like what the different values should be and how the phase noise or noise in different components affect the jitter, etc. Okay? Any questions here? I think everything that I said so far is probably familiar to you from communication systems, etc. courses. And then, this is just a refresher, and then we will be using this heavily for modeling clock and data recovery circuits and phase lock loops. Okay. So let's do that. Let's first take I'll take a linear phase detector, okay, which gives out the up and down signals. We know that basically if there is a phase difference between data and clock, okay, there is a phase difference between data and clock, you will have both up and down pulses, but the average will be proportional to the phase difference. Okay. And this control voltage we controls that one, and I'll assume that as usual this delay decreases with V control. Okay, that is just my convention to reflect reality. Normally if you make a delay line, if you increase the supply voltage, which is the control voltage, the delay actually reduces. Okay. So I will say that this delay is some constant minus Kd times V control. Okay. So that is the delay versus V control falls like that with a slope of Kd. Okay. Is this fine? So now how do we go about modeling this? First of all, one thing I have to mention is, so far I have considered periodic, I showed periodic signals and its phase, right? We discussed that. Now what happens when you have random signals like data? How do we deal with that? Can whatever we discussed so far be also used with data? So essentially, each period of the data, each symbol interval also should be constant, right? So you can represent the ideal data phase of the data as marching off as a straight line. Now because data does not have all transitions, that is random data will only have half the transitions, you are not sampling it at every one of these instants. You are looking at where like maybe you omit some samples, that's all that's there to it. Otherwise this picture applies even to data. Okay? Is this fine? So now let's see, I will call this, first I will call this theta d, okay, and this is theta in, maybe theta clock in or theta in, and then this is phase of the clock. Okay. Now at the operating point, right, that is when this whole thing stabilizes, let's assume that it stabilizes correctly. Where will it stabilize? This the clock edges will be in the center of data, right? So ideal, and you can for now assume data to be like an alternating signal, that is it's actually a periodic signal, 1010 signal. Okay. That is if data looks like this, the clock would look like that. I mean later when you are dealing with phase offsets and so on, you can also incorporate that into it. Okay. So this is my operating point. I am doing this, I mean this is something you are familiar with, right? In circuits you first compute the operating point and then you find deviations from there. So my operating point is the input data has no jitter, the input clock has no jitter, okay? But it has some phase offset and my CDR will adjust the delay so that the edges of this clock are in the middle of the data as you want, okay? So this is the operating point, okay? So now what you can do is the following, right? You can have so this is for analysis. I'll assume that, for instance, there are some edge positions, the transition positions of the data deviate from the ideal ones. That is, it has some jitter, let's say, okay? So the data should have transitions at some instances, but it can move back and forth because of some noise in the transmitter or whatever, some jitter, okay? So that will appear there, right? Alternatively, you could also have the clock that is coming in could have some deviations. It's not quite periodic, so it will have some deviations, right? The clock edges can have that. Is this okay? So now what do you expect when either of these things happen? Maybe it is both or maybe it is either one of them. You expect that every one of these quantities will have some deviation, okay? So maybe I will represent the operating point with uppercase and the increment with lowercase, okay? So everything will have some deviation. Now what is it that you would ideally like? Let's say the data edge, the data symbol moves, okay? The clock that is sampling it should move along with it, but we don't know whether that will happen, whether it will move by that amount. So what I am doing is, I'll assume that the data edges move by some amount, which is represented by this phase deviation, or the clock edges move by this amount. Then I expect deviations in everything, okay? In fact, there is only the phase of this and the phase of that one, okay? And then I find the relationship between these incremental quantities. So when you say a phase model of a clock and data recovery circuit, that is what it is representing, okay? So you have some operating point, which is the locking point of the CDR. In the ideal case, that is when the rising edges of the clock are in the middle of the data interval, and then you have deviations from that. This could be due to anything. I just took two examples when the input data has a jitter or the input clock has jitter, but it could be neither. For instance, it could be that these current sources are noisy, right? That means that when up switch is on, it's not just ICP plus, it is ICP plus some noise. Similarly, when the down switch is on, it is this ICP plus some noise. That itself you expect to create deviations. I mean, it won't create deviation in the input, but it will create deviation in this control voltage as well as this sampling clock position, right? So that also causes jitter. So all those relationships can be found out from this incremental model, okay? Is this fine? So how do you do that? All you have to do is to mark every quantity in the picture, right? And then take only the increments and see the relationships between them, okay? So ideally, what is the current that is flowing here? The average current that is flowing there, flowing out of the charge pump. At the ideal operating point, what is the average current flowing out of the charge pump? 0. I mean, that is why it is the operating point, right? Because the average here is 0, V control is a constant. If the average was not 0, it would keep ramping up or down. So this is ideally 0, and then you expect that it will also have some increment, okay? So now what I have to do is I just have to represent the relationship. I mean, basically like what you do when you have a circuit. You have a transistor, you have a resistor, you have a number of other components. And when you have increment in VGS and VDS, you have an increment in the current. So that is represented by the small signal model of the transistor. Similarly for a resistor, a diode, etc., etc. So that's what we will do for every component here. We just want to find the relationship between the input and output increments. Okay. So the reason I am emphasizing this is sometimes it's not clear the phase model of the clock and data recovery circuit or the phase lock loop is given, but it's not clear what it is modeling. What it's modeling is it has some operating point and over that you have the increment. The operating point I have now considered to be the ideal one where the clock is in the center of data, but it could be deviated also because of some offset or something. But you can, for the new operating point, you can find the incremental model. Okay. So let's start with let's first start with maybe the phase detector. Okay. Phase detector, okay. Yeah, we can take the model of these two together, for instance, right? The inputs to that are this lowercase phi d and phi ck, and the output is this ICP. What is the relationship between these? ICP is the this current that is shown here is the average current. I am not interested in the instantaneous current, right? Because it's the average current, that's a measure of the phase. The instantaneous current I can add it later as an increment. Okay. So what is the relationship between phi d and phi ck, which are the inputs, and ICP? We have derived the model, right? What is it? What is it? ICP equals phi d minus phi ck multiplied by 2 pi divided by 2 pi. That's it. Times ICP. Obviously, the dimensions also have to be correct. So this is what it is, right? So what is this? If I had to draw a block diagram for this, it would be phi d phi ck, and this is the phase difference, and that is multiplied by ICP by 2 pi, which is the gain of the phase detector. Okay. This gives me ICP. What is the incremental model of the capacitor? What is the incremental model of capacitor? Capacitor itself. I mean, any linear element, its model is itself, right? Okay. You can write it like this, or you can show it as ICP as input and 1 by SC as the transfer function, and the control voltage as the output. Either one is the same thing. I mean, it will be obvious which is which. Okay. So if I show this as a current, then if I show it as sort of signal flow block diagram, it will just be ICP followed by a transfer function. Okay. What is the model of this delay line? So again, what I have is this is going through a delay line. Okay, and the output is okay. So what is the model for this? So first of all, what is the relationship between these two? What is the relationship between theta ck and theta in at the operating point? What happens when you delay? What happens to the phase? Huh? 2 pi times? Yeah. So basically, this time delay Td This means a phase delay omega naught Td, right? Okay, so this is equal to phi n minus omega naught Td, okay, which is basically phi n minus omega naught, and this Td itself is T naught minus Kd times the operating point control voltage. Okay. Now if I add the increment to that, what happens? It is again the same thing. I have this is theta Ck, this is phi n, and now this will be this minus again omega naught Td, right? And now Td is omega naught T naught minus Kd times the operating point V control minus Kd times the incremental V control. Okay. So if I take the relationship between only the incremental quantities, I will have phi n minus omega naught, plus omega naught Kd V control. Is this okay? I mean, please derive this yourself. I don't know, from your reactions I am unable to tell whether you are able to understand everything or nothing. Okay. So all I am doing is the same thing. I wrote the operating point equation, I wrote operating point plus increment, I subtracted one from the other to get the relationship between only the increments. Okay, so that's why the operating point that we control, all those things go away. I am only interested in the increment. The operating point we control, that is the operating point we control required to set the clock in the middle of the data. It could be half a volt, it could be 200 millivolts, whatever. That's not relevant. Only the increment is what appears in the model. So how does this come out now? So this phi Ck will be this V control multiplied by omega naught times Kd added to the input clock phase phi n. Maybe I should denote it by phi Ck in to make sure that it is the clock phase, and fed like that, right? So this is now the incremental model in the phase domain of our clock and data recovery circuit. Okay. Now from this, what is the relevant quantity here about whether the clock is in the correct position? It is phi d minus phi Ck, right? This phi d minus phi Ck should be 0, that is incremental phi d minus phi Ck. That means that the clock is in the correct position, in the same position as the ideal operating point. If this phi d minus this phi Ck is something other than 0, that means that clock has moved from the ideal position. Okay, and that's what we can see, like how much it moves. It can move in response to changes in phi d, it can move in response to changes in phi Ck in, it can move in response to noise in the blocks that you use to make. Okay, that is either in the charge pump or in the delay line. Okay. So now, I mean, once you have this, it is a trivial linear systems type problem. You can find the transfer function from this phi d to phi Ck into phi Ck. You can add some current noise here, from that to phi Ck. You can add some noise in the delay line. That is, the delay itself will not be constant. Okay, because of noise of the transistors used to implement the delay line, the delay itself will be jittering around. So you can add that as a phase noise at the output or a voltage noise at the input, and you can find all those transfer functions to see how they behave. Okay, so we'll do that in the next class. So basically the point is, in presence of either the input jitter or the input clock jitter or the noise in the circuit components, the clock will not stay in the middle of the data symbol. It will move around. So we have to see how much it moves around. Okay. So, and then, I mean, like I said, one of the more basic things is to find out how much ICP should be, how much C should be, and so on. Right? So those things will basically, we'll basically get by analyzing the incremental model. Is this okay? So if you please think about this and derive the model by yourself. If you have any questions, we can discuss them in the next class.